Welcome. This instructional video is going to prepare you to do well for your lab practical. About 33% or 1/3 of your overall exam grade will be calculated from your lab practical exam. You have in front of you your exam review packet, and this information is going to help you prepare for each of the 4 categories we will go through in our lab. Let's talk about that general information. Your lab practical will be part of your exam grade, along with the written section. Again, about 1/3 lab practical, 2/3 performance in a written test. You're going to be assigned lab groups for this experiment. Now, most likely these will be the groups that you've worked with all year, but I do this just to ensure that there's no more than 3 to 4 people per lab team. In the first hour of our 2-hour block, you and your team will conduct a 4-part experiment. You'll be generating data and making observations together as a team. Then in hour 2, we will come back into the classroom, and each student on their own will be writing their own lab report, processing the data that you recorded from the lab. You will not be allowed to ask your team members for any information once we enter the room for hour 2. Be sure that you walk into the classroom after the lab hour that you have everything written down on your own paper. I am also going to make sure that you are not seated next to anyone from your original team. That helps me ensure that you're indeed processing the material all by yourself. There is a 4-part lab practical. In part A, we work a combination reaction. In part B, a decomposition. A part C, a single replacement. And in the part D, we work a double displacement reaction. I'm going to talk you through each one of those 4 components, and we'll write down some sample data questions together. In the part A, the combination reaction, we've done this experiment. It's probably before our first semester exam. In the combination reaction, let's read these words carefully. You will be reacting tin metal with oxygen from the air. We've just been told our reactants for the combination pattern. Tin metal with oxygen from the air. In this combination pattern, 2 elements combining to make a single product. We use a catalyst. The catalyst is called nitric acid. We pour the nitric acid underneath in the fume hood onto the tin directly. It will start to react. If you recall having done this experiment earlier, the tin starts to bubble up and a brown heavy gas starts to come out of the evaporating dish. It's stinky, which is why we're doing it underneath the fume hood. Please note that this is a quantitative experiment. This means numbers are important. The more accurate your experiment is measured, the better your lab results will be. So a combination reaction. Please note there's an announcement on. Let's take a closer peek at more examples. Keep in mind just a general idea of what we've done. Here's the skeleton. Tin metal starts as a solid. We want to react that with oxygen from the air. There's the gaseous form of oxygen. Not only to force the combination of the 2 elements do we heat it, remember that triangle stands for heat, we also catalyze it with nitric acid, HNO3. So 2 individual driving forces, additional heat and a catalyst, HNO3. Purpose of our experiment is to determine the empirical formula of our compound, SN something, O something, where those somethings are called whole number mole ratios that work to the lowest mole ratio for subscripts. So we're looking for a tin oxide product. This is a great example of sample data that allows us to practice the type of calculation you'll be asked to perform. One of the procedure steps will have you weigh an empty evaporating dish with a cover, a watch glass cover. You pour in approximately 2 grams of tin and weigh it again, and we want to know the mass of tin. Of course, here it's line 2 minus 1. So what is the difference between 76.2 and 74.14? We weighed out 2.06 grams of granulated tin. Now you're going to be asked to show how to convert moles or mass of tin into moles of tin. So just an old mole map formula, but be ready that you'll be asked to show your work. Number, label, unit. We have 118.7 grams. Oh, I'm so sorry. I just wrote that on the wrong spot. If you're like me, you have an eraser. We want to convert into the mole, and the molar mass of tin goes on the bottom. So just looking off the periodic table, molar mass of tin, 118.7. So let's divide that out, 118.7, and we find a number, 0.0174. Carry all of those decimals with me, and those are your moles of tin. So from there, be sure you also write it up here in your data table, because that's where I'll be checking for the correct answer. Now, this is where we begin the actual reaction then. So far we've just walked to the scale, weighed out some tin, and did a mole conversion. Now we want to force it to oxidize. So after weighing the tin, you'll be instructed to go to the fume hood and pour on nitric acid. Be a little patient because it starts to bubble, and you want to let it go a little bit so that you don't have to breathe so much fume at your individual table. Let it get going and then kind of settle down before you go back and put it over a flame at your desk. Now remember, you were instructed to cook it so long that the tin oxide product actually turns a little bit yellow. Starts kind of as a white powder after you pour the acid on, but cook it strong enough until you see that canary yellow. Not a little yellow, but a lot of yellow. That's when you know it's good and dry. Shut the flame off and you let it cool. When you let it cool, the final weighing, 76.76 grams, the very final weighing. That is the tin oxide product sitting in a dish. So how might we calculate the mass of the oxygen? And then the moles of the oxygen. This, by the way, should be a mole unit. Please repair that on your paper. So the mass of the oxygen, notice here we can figure this out because we know the mass of the dish and cover, mass of the dish, cover, tin oxide. So let's begin by subtracting that final weighing, 76.76, minus the original dish, 74.14. That tells me that my tin oxide product was 2.26 grams. That's tin and oxygen combined. Now let's subtract how much original reactant there, and what do we have? It's exactly 0.56 grams of oxygen. That the mass of the oxygen plus the mass of the tin is equal to the mass of the whole product that I weighed in the dish as the final weighing. That's the law of conservation of mass. This 0.56 grams of the oxygen that's combined on the tin needs to get converted to a mole. We always use atomic mass, not molecular mass, atomic mass, because it's not as a molecule anymore, it's attached into a compound. So we use 0.56 divided by 16 for the oxygen's weight, and our number of moles that combined on are 0.035 moles of oxygen. And be sure that you write that up here, 0.035 moles. So here's what we're noticing, my moles of tin and my moles of oxygen. Bring those down and rewrite them with me for number 3. We have 0.174 moles of tin and 0.35 moles of oxygen. We want to turn those into a formula, and the way that we've learned that is to divide both through by the smallest number, so it becomes the 1. How many times does our smaller number go into the larger number? 035 is the larger number. I'll divide that out by 0174, and I find a number 2.01. So I'll call that 2. Our mole ratio is 1 mole of tin for every 2 moles of oxygen. We'll then be asked to simply write the formula. 1 mole of tin with every 2 moles of oxygen is SnO2. Don't forget to name it, including the Roman numeral. Now keep in mind, oxygen is always a -2 when it's hooked in a compound, so the total net negative is 4. What's the charge on our tin? Well, it's got to be a +4. Naming my compound and requiring that Roman numeral, we've made tin 4 oxide. My correct name and my correct formula, SnO2. In Part A, we can't stress enough how important it is to take accurate measurements. Make sure you have plenty of drying time. Make sure that you've dried enough to where you're seeing a nice bright yellow color. Then take your final weighing. You should practice with this data table until you feel confident that you could process it without any help at all. Remember, this is going to be turned in before you take your test. You're not allowed to use this. It's a practice. So turn this video on, pause, practice this data table, and pick up with Part B when ready. Well, I should have noticed there's 2 more questions. I'm sorry. Let me finish processing before you pause. To determine the percent composition using your mass data, I need to go back to my data table. Here we had 2.06 grams of tin. I'm going to record that. From the data table, we recorded 2.06 grams of tin. And from the data table, 0.56 grams of oxygen. To calculate the percent of tin, I want to know its contribution to the total mass. So the sum was 2.62 total grams, adding these two. So the percent by mass of tin is its percent, 2.06, over the total mass, expressed as a percentage. And if oxygen contributed 0.56 over the 2.62 grams, expressed as a percent, what did we find? Remember both answers. 2.06 divided by the total mass of 2.62, expressed as a percent, 78.6% by mass tin, and 0.56 divided by 2.62, expressed as a percent, and we have 21.4% oxygen. And just to remind us, we did this above on the previous table, including adjectives. It will ask us that, so do stress that. Granular tin is solid state, gaseous oxygen, combined in the presence of heat and in the presence of a catalyst to form our solid yellow compound, tin 4 oxide. Now my particular data balanced. Now we've made it through all of Part A.